Alright, so today we're doing substitution rule, and the substitution rule is sort of the same as chain rule for derivatives. So some of my students have referred to it as the reverse chain rule. I particularly don't like that name, but it's close. The definition for the substitution rule says if I have an integral of some function f, and inside of that function is another function, g, and I also just happen to have the derivative of g lying around in my integral, then I can call u g of x, and the differential du is the derivative of g times the differential dx. And that'll be true as long as the function and its derivative appear. Now, there are times when this g prime is nothing more than a constant. If the constant is not already in the integral, you may introduce it. If g prime is some function of x that is not just a constant, so x squared, for instance, you may not introduce that into the integral. If you make these substitutions, you can rewrite this as the integral f of u du. So the goal here is to take something that we do not know how to integrate and make it look like one of those functions that's in that list of ours for the basic integrals. So let's try a few and see if this starts to make some sense to you. And as always, please ask questions if you have them as we go along. So the first problem here is integral 2x times x squared plus 5 to the 9th power. My guess is that some of you are going, oh, well, that's not bad. We could just multiply this 2x in here and integrate each piece. But this is to the 9th power, which means you'd have to multiply this binomial by itself 8 times and then multiply by 2x before you could start integrating each piece. So this is not something that we can solve very easily by expanding. However, notice I have a function inside of another function. So if I were to let u equal everything inside these parentheses, then the derivative of x squared plus 5 is 2x. So du is going to be 2x, and then because it's a differential, it needs a differential on the other side. Because this is with respect to x, we get dx. If you don't like this, what I've seen a lot of people do again is say take the derivative of this with respect to x and then move the dx over afterwards. So if you want to do that to start, while you're getting used to it, feel free. But that's really all we need right there. So then the question is, do we have all of what we've just created here in the problem? Well, I see a 2x there, and I see a dx there. So all of this is my du, and everything inside of here is u. So this integral becomes the integral of u to the 9th du. Right, because this here is u, and these two things are du. Any questions about that, guys? All right. So I don't see any questions, so I'm going to go ahead and continue. So this is now one of those integrals that we see in our chart. It's the power rule for integration. We add 1 to the power and divide by that number. So this becomes u to the 10th over 10. Because it is indefinite, we need plus c. The last step is to take whatever u was, right, whatever we set u equal to, and plug it back in. Our problem started with x's, which means it should end with x's. So this is now x squared plus 5 to the 10th all over 10 plus c. Right. Excuse me. Now I would typically give this next problem to you guys to do, but because of the current situation, I'm going to go ahead and do it. But I'll go ahead and I'll ask anyway. So let me write it here first. Is the integral e to the tangent of x times secant squared dx. What would you let u equal in this problem? And what would du equal? So I'll give you guys a second to answer that question. So I see two possibilities so far. Anybody else? So remember, we want u to be something that is inside of another function, potentially, or a function whose derivative is present. So I'm going to let tangent equal u, because the derivative of tangent is secant squared. And therefore, this is e to the u, and all of this is du. And the integral of that's easy. All right, we all love it. It's e to the u plus a constant. And finally, let u equal what we set it to earlier. And that's your final answer for that. So the first two had functions inside other functions. This does not have a function inside of another function. And I need my dx here. So instead, I just need to let u equal some function whose derivative is present. So would you let u equal the numerator or the denominator here? So basically the question is, which one of these functions is the derivative of the other? All right, so yes, I would let the denominator equal u because the top is the derivative, correct? So let u equal x to the fourth minus 5, and so then du, its derivative, right, is 4x cubed. And of course times dx. So all of this is du, and that is u. So this integral becomes du over u. Do we recognize that integral? So that is the natural log. Right, it's 1 over u du. Remember to get the absolute values. And always the last step is to back substitute for u. So you get that. Okay. So I think what I'm going to do is I'm going to finish out these problems today. And then next class I'm going to give you a list of maybe 10 more problems to do, or we might just do the suggested homework for this section. And I want you guys to work them out and ask questions, so we might meet in a different capacity. But it's very important that you guys know how to do this, especially if you're going on to Calc 2. Pretty much every section of Calc 2 that I teach and that I know of anybody else teaching, they expect you to know this walking in the door. So day one, they review this and start something else the next day. Where did the ln come from? So that was the integral of 1 over u du. If you look that up in the chart that I gave you from the first day of integration, that integral is natural log. Remember that the derivative of natural log is 1 over u. So if we go the other direction and integrate, we get back natural log. If that didn't help you, let me know. Okay, so here's an instance where you may not know which one to choose. You may not see the one that has its derivative here. So typically a good guess is everything inside of a set of parentheses or anything that's to a high power. So I'm going to let the natural log of x here equal u. And the derivative of that we just discussed is 1 over the inside. And because it's a differential, I get back dx. All right. So the question is, do you see that 1 over x dx is here? All right, if I rewrote this, maybe you'll see it better. All right, I can divide by x, or I could multiply by 1 over x. Either way, it's du. And everything inside the parentheses is u. So this integral is now u to the 5th du. Again, we add 1 to the power, divide by the number. So u to the 6th over 6. We always need our plus c if we're indefinite. And last thing is to plug back in for u. So natural log of x to the 6th all over 6 plus c. Any other questions about that one? Okay. So the next problem is integral x to the 6th sine of x to the 7th dx. So again, what would you let u equal, and what would du equal? Who wants to try? Okay. So because this power is lower, the derivative of this guy becomes that guy, right? Because it's one power lower. So if I let u equal the inside here, x to the 7th, my derivative is 7x to the 6th, which is my guess for your hesitation, because x to the 6th and dx is there, but there is no 7. So that's what makes this one a little different. And you may recall at the beginning I said you can introduce constants, but you may not introduce functions of x. So it is perfectly fine for me to plug a 7 in here, but I can't just put a 7 in there and forget about it. I have to do the opposite on the outside, because I've effectively now multiplied by 1, right? 7 over 7. So I have 1/7, 7x to the 6th dx is all du. And I let that equal u, so I still have the sine of u. That is a basic integral. The integral of sine is minus the cosine. And finally, plugging back in u and pulling this negative out in front. This would be my answer. So I'll leave that one there and I'll start the next one. So again, this one might be kind of hard to decide. Or you could try and let u equal x squared, but your du, would be 2x. There is no 2x, there's no x, right? There's 1 over x in there. So I would think that letting everything be u that's inside the parentheses is a good choice. Du then is going to be the derivative of this, which is going to be, and if you want you could write this as pi x to the negative 1. So remember, you bring the negative 1 down and make this to the negative 2. So it would be that. So the question from the last one was, why did you add the 7 and the 1/7? So if I let u equal x to the 7th, then the derivative of that is 7x to the 6th. I already had x to the 6th. I did not have the 7. So I can introduce constants. So I put the 7 in, but I'm not allowed to just multiply by 7. Right, it's like I tell you the answer to the problem is 10. And then you just, for no reason, multiply by 7. Well, then you have 70. That's not correct. But if you multiplied by 7 and also 1/7, right, they cancel and you get 1 out of that. So I'm allowed to introduce constants into the integral. But if I do that, I have to put their reciprocals outside. So I'm going to have to do that again here, right, because my derivative is minus pi over x squared. Well, I've got 1 over x squared here, but I am missing a negative pi. So before I can substitute anything, I need to introduce a negative pi in here. So again, if you want, you could write the cosine off to the side and then say times 1 over x squared dx. So as I said, I'm missing the minus pi. So I would, inside here, multiply by minus pi. But I'm not allowed to just do that. I have to do the reciprocal on the outside. So over here, I have to multiply by 1 over a negative pi. So du is minus pi over x squared dx. That's all of this. And pi over x is equal to u. So this is going to turn into cosine of u. And I have this minus 1 over pi on the outside. So this all reduces to this, and that just came down. The integral of cosine being sine. So we get minus 1 over pi sine of u plus c, and the final step is to plug back in u. So sine, and u is equal to pi over x plus c. Let me just go ahead and rid this for a second, in case you were trying to look at just that one. They were kind of cramped there. So any other questions about this guy before I move on to the next one? All right. So again, I need to let something equal u. Right, and again, this is why we call it u substitution. So let u equal, and then we need to find what would be the derivative of that. So I'm going to let u equal x squared, because the derivative of x squared is 2x dx. I've already got an x here. I am only missing a 2. I can introduce that 2, right? I'm allowed to put a 2 inside here. But if I do that, I have to counteract it with a 1/2 in front. Once I've done that, I can rewrite the whole thing in terms of u. So 2x dx is all of du, and e to the x squared is e to the u. And that's just one of the greatest integrals of all time, because it's just e to the u. And we plug it back in, and we're done. And so all of these are a puzzle. It's where is a function whose derivative appears or almost completely appears minus some kind of constant multiple. And if that's the case, then we can use the u substitution and go from there. So that one's really not that bad. All right, so anything appear different to you about this problem? So the thing you should notice is now I have bounds, right? So when I start adding bounds, I no longer get any plus c's. Come on, camera. Here we go. Same procedure. Let u equal something, solve for du, and it better be in the problem. So again, u is most likely a good option to let whatever's in the parentheses be it. So this would be x cubed minus 1. The derivative of that is 3x squared dx. Now I've got x squared dx already. I need to introduce a 3. So I put that in. And on the outside, I would put a 1/3 to counteract it. So this is now equal to 1/3 integral. My 3x squared dx is all du. And the parentheses x cubed minus 1 is all u. So I get u squared du. And if it helps you, you could always rearrange this stuff, right? I could rewrite it like this. As long as the dx is the last thing, you can rearrange it. So notice I haven't written the bounds yet. There are two ways to continue. I can put placeholders here, a and b, and when I convert back to x, I can plug in 1 and 2. Or I can change the bounds. So what does a u substitution really do? Well, the idea is that we're going from some space that's x, y, and we're changing it to a new space that's now maybe u and y. Or actually, I guess x and u, if you want. So the whole point there then is, if I'm changing space, well then the values that I plug in for x here don't qualify for u. So I can change them by plugging each one of these bounds into this equation, the one equation that relates the two variables. So, what is u when x equals 1? Well, that's 1 cubed minus 1. That's 0. So my bottom bound for u is now 0. And what is u when x equals 2? Well, that's 2 cubed minus 1, or 8 minus 1, which is 7. So the upper bound is 7. So I do not have to back substitute at this point. I've turned my values into u, so I can integrate. And I can plug in for u. So this would be u cubed over 3. And then I need to plug in my bounds. So I'm going to make this 1/9 times u cubed from 0 to 7. So that's 1/9. 7 cubed minus 0 cubed. So what is 7 cubed? $343. 343 over 9. And does that reduce at all? Nope. So it looks like that is our answer there. So let me go ahead and do it the other way as well. So I could have integrated, back substituted for x, and then use the old bounds. So the other way would have been, would have had 1/9 u cubed, replacing u with x cubed minus 1. So x cubed minus 1 cubed from 1 to 2. So plug in again. So 2 cubed minus 1, quantity cubed, minus, plug in the lower bound, 1 cubed minus 1 cubed. That's 0. This is 8 minus 1 is 7. 7 cubed is 343 over 9. So you can do it either way. It is up to you which one you feel most comfortable with. I personally think it saves some time to plug in the numbers here so that there's less that you have to plug in at this point. Right, it just looks a little more daunting when you do it with X. But again, whatever one that you feel more comfortable with. If you don't, a lot of people have trouble for some reason deciding what to plug these numbers into, and it's always the equation of u with respect to x. Right, the very first thing that you choose, that equation right there is what you plug these numbers into. So I plugged 1 in there, and I got 0. And I plugged 2 in there, and I got 7. Any questions about that problem? And I'll wait a minute to see if you guys have any questions. How many problems do we have left here? 2. 6 more. Alright, so I guess you guys are okay with that problem. So I suppose I will continue. How did you get 1/3 u cubed over 3? Alright, so hopefully we're okay with the fact that I put a 3 in here for du, and when I did that I had to put a 1/3 in front to counteract it. And then the 1/3's already there. U squared. When you integrate, you add 1 to the power, which makes it u cubed. Divide by that number is 3. And then 3 times 3 makes it 1/9 u cubed. Okay, so what was your other, did that answer your question? Okay. Alright, we got the integral 1 to e cubed Alright, so we've done this one earlier, we just didn't have bounds. Remember, we let u equal natural log of x because the derivative of that is 1 over x dx, which is right here. So everything I need is already there. I don't need to introduce anything new. This is just the integral of u du. So how about this time I'll just put placeholders, a and b. I'll do it that way first. Integral of u is u squared over 2, evaluated from a to b. And if I plug back in the definition for u, I can then use the bounds for x. So this is natural log of x squared over 2 from 1 to e cubed. Plug those in. Natural log of e cubed squared over 2 minus natural log of 1 squared over 2. Natural log of 1 is 0. Natural log of e just returns the power. So that would be 3 squared over 2, or 9/2. So that's one way of doing it. What if back here I changed my bounds? Okay, so let x equal 1, u then is natural log of 1, which is 0, and let x equal e cubed. Natural log of e cubed is 3. Integral of u is still u squared over 2, but this time it's from 0 to 3 and we don't have to back substitute. Plug in the numbers directly. Same thing, right? So like I said, I think, personally, I like the change of bound rather than back substitution, but it's all up to you, whatever you feel more comfortable with. So I've got 2 more of these with bounds, and then 1 more topic, and then we'll call it a day. And as I said, next time I'm just going to give a bunch of problems for you guys to work on, and I want you to, tell me what you're not getting, and hopefully we can get you integrating pretty quickly. Okay. So next one involves a trig function. So we'll actually find that in Calculus 2, there's a whole nother topic of integration called trig integrals, and this is technically one of them. But in all reality, it's just a u substitution. So sine to the 5th cosine dx. I'm hoping it is clear to you which one to choose for u. All right, we have to have a function and a derivative there. So yeah, technically the derivative of cosine is minus the sine, but we have 5 of them, not just 1. So we should let u equal sine of x, because remember I could write this like that. Du is the derivative of sine times the differential dx. And we have all of that in our integral. Right? We've got u right there, we've got du there. So this integral is now u to the 5th du. Now the only thing is that this is not going to give us a nice number when we plug in. So I may leave it as sine of 2. Let's see. If we plug in 0 here, right, sine of 0 is 0. That's not bad. But the sine of 2, that's not a nice number. So I'm just going to leave the bound as sine of 2. That's an easy integral. You add 1 to the power, divide by that number, and then evaluate from the two bounds. So this would be sine of 2 to the 6th over 6 minus 0 to the 6th over 6. So obviously that's 0, and that is our answer. So not pretty, maybe not what you expected, but the solution nonetheless. All right, one more example of this. The integral from 0, looks like to pi over 3 tan x secant squared x dx. So again, we're looking for a function whose derivative appears. The derivative of tangent is secant squared. So if I let u equal tangent, du is very easily secant squared dx. So all of that is du, and that is u. And therefore this is very easily translated into u du. The only thing we have to then change would be the bounds. So tan of 0 is 0. What is tan of pi over 3? So take square root of 3. Okay. So this would be u squared over 2 from 0 to root 3. Plug in. Looks like you're just going to get 3/2 out of that. So any questions about any of the problems I've done so far? Anything else you need to see, confused about? So I got one more topic to cover. I think I might only do 2 of these and leave one of them for you for tomorrow. So this is called change of variables. We've been doing U substitution, but sometimes there are cases where we can use U substitution, however, it's not as simple as just turning it into some integral of U du. And by that I mean there's a complication. So let me look at this one. Okay, I've got a radical. I've got my dx there, and I got this x on the outside. So naturally, you should want to let u equal the inside under the radical. And that is in fact a good choice. But what happens when I differentiate 2x? Well, I get back 2. Okay, that's great. But I've got this x out here that I don't know what to do with. So this is why they call this one change of variable. Everything under here is u, and I've got an equation right here that's relating u and x. Because I have an x lying around, if I solve this equation for x in terms of u, I can substitute it in. So this would be u plus 1 divided by 2 if I solve that for x. So now let's substitute for everything here. And actually, before I do that, my du does need to be 2 dx. So I'm going to multiply by a 2 in there, and therefore put a 1/2 out in front. So now I'm just going to substitute for everything. X is equal to this. Everything under the radical is equal to u. And 2 dx is du. Okay? So you should see that that integral now is all in terms of u. So then if I'm going to pull this 1/2 out in front. It's just a multiplier. So that makes it 1/4. And I'm going to make this square root into u to the 1/2. Then I'm going to multiply this in, right, distribute. So u times u to the 1/2 is u to the 3/2. U times 1 is u to the 1/2 there. And then all times du. Then integrate them. Make sure I'm not going to go off the screen here. Okay, I'm good so far. So integrating u to the 3/2, I add 1 to the power, so that makes it 5/2, divided by 5/2, and this one would be u to the 3/2 divided by 3/2. And then I need plus c because there are no bounds. I'm going to come back up over here. Let's see. I just want to... So dividing by 5/2 is the same thing as multiplying by 2/5. And And then the other one is multiplying by 2/3. And the reason I did that is because I have a 2 here on both of these that I can cancel with one of those. And I'm going to leave the answer as this. Well, not leave, because I have to plug the u back in. So doing that, u is equal to 2x minus 1. I know I did that last little bit there fairly quickly, but it's some basic algebra. Alright, instead of dividing by 5/2, I multiplied by 2/5 and 2/3, and then I just factored out a 2 and canceled it with the 1 in the denominator. And then the last step was just plug in for u in both cases. This is my answer to this integral. So any questions about that one before I do the last problem for the day? And I know I've done a lot of them, but you really do need a lot of practice with these. So I haven't seen any questions, so I'm going to go ahead and do this last one, and then I'll open the floor to you if you have any questions. I think maybe you're just trying to take this all in. Alright, so last example. I have the integral of x squared square root 2 minus x dx. I'm going to let u equal 2 minus x. Du is minus 1 dx. So I need to introduce a -1 in here, and therefore a -1 out there. It doesn't matter if I divide or whatever on the outside, it's dividing and multiplying by -1 is the same thing. So now I have this x squared I have to worry about. So I take this guy and say x equals 2 minus u, and so x squared is just 2 minus u squared. Make all the substitutions. This is minus an integral. For x squared, I'm plugging in 2 minus u squared. The square root is now square root of u, and -1 dx is du. So I'm going to FOIL this and make that into 1/2. So this is 4 minus 4u plus u squared, and this is u to the 1/2. Multiply that through, like that. Finally integrate it. So all I did here was, instead of dividing by 3/2, I just multiplied by 2/3, and same thing, right? Instead of dividing by 5/2, multiply by 2/5, and so on. I think I'm going to factor out a 2 out of the whole thing. So this is going to be 4/3. And u is equal to 2 minus x. Actually, let's factor out a u to the 3/2 as well. So u is equal to 2 minus x to the 3/2, and then inside we've got 4/3 minus 4/5 times u plus 2/7 times u squared. I'm sure there's some other way to write that, but for now I think that's probably good. You could technically multiply all this out and try and simplify, but I am perfectly happy with that form. So, can I help you guys with any questions that you may have? Alright, so I'm going to go ahead and stop the recording.